I sent, I don't know whether you have gotten it. I sent an R code to the platform that we are going to run. Okay, it's already there. Did you get it? So we are going to run the event-based stochastic simulation for the SIR model, giving all about 6 events, which involves the matrix, the EMAT, and then we have the various arguments in the function. So the first argument is rat equation, that's rate equation, a list of rate equations corresponding to each of the possible events using the code formalism. And then we have the event matrix, which is an A by S matrix of changes to each of the S state variables associated with each event. We have the parameters, so a vector of parameter values, the initial values of the states variables, and then the number of events to be simulated as the arguments. So for the Gillespie function, algorithm, it's an algorithm that involves the function of all the arguments. The arguments are rat x, event matrix, that's rat equation, the equations in the model, the events which we form matrices, the parameters which are beta, gamma, and all of that, the initial values, that's initial states variables, and then the number of events. And then we form the data frame of matrix, and then with the object name res. So, and then we have all of this. So the parameters are there, which are mu equals to 1, beta 500, and all of that. So, and then we have the simulation, the Gillespie, which contains the R list, the EMAT, which we have defined earlier, the paras, which is the parameters. So we provide parameters and initial condition for a stochastic simulation. And then we have the math plots. The math plot is the sim. Now, if you run this sim, you are going to have about 4 different variables, including the time. The time is the sim of 1. And the SIR, the 4. So that's from 2, 3, 4. And then you have the time for this. So it runs everything together. The Y lab is the number, which is the y-axis. The type we want is the line. We want a line. And then the X lab is the time. And then it's transformed. So we transform the y-axis with logarithmic transformation. And then we have the legends. The legend there is as the way we want our SIR to be placed. So on the graph. So, and then we have the column is 1, 2, 3, and all that. So we are going to run this, and we are likely going to get something like this. Now, if you know your former SIR that you did, cannot give you this because this is a stochastic model. So it's giving you with the noise. So you find out that for your SIR model, you are having a straight line, normal straight line. But this one is different from that because this is giving you a form of the noises involved. And then it also depends on the number of times you are running this. You get more So we are going to be changing, and then you'll be seeing different kind of shapes and all of that, the ranges and all that. Um, so let's go to the lab. So um, so we have the R list, which is a list of equations corresponding to the rate of for the sixth transition of the SIR flows. The code formalism allows us to set up the list such that all the equations can be evaluated in a single S apply call for the simulation progress. So now we have this, which is the R list. Now it contains the bets, mu, S plus I plus R. And then we have the mu X, which is susceptible debts. And then we have the beta SIR. We have the mu I. We have the gamma I. We have the mu R. So all of these are the events. So in the model, so all the events in the model, we have about 6. So I'm going to run that. So do you have the code already? Have you started running? It's inside the WhatsApp platform. So you have, so for the first about the matrix, you have the rows correspond to 6 possible events. So you have the first one is the bets, which happens to be in the susceptible class. That's the first event. So we don't have that bet in other classes. So all the rest are zeros. Then the second is the dates, which also happen. That's the mu. It only happened, mu s only happened in the susceptible class. So -1, others are 0. And then the next one is the transmission, which happened in the susceptible class and also in the infected class. So you have, so for that, you have -1, 1, and 0. And then the next one is the deaths of the infected. So you have -1, and then others are 0. And then the next is the next event is that's gamma I. So gamma I is recovery from that's natural recovery from coming out of the I class and going into where? The R class. So that's for I is going to be -1, for R is +1. And then the last one there is the gamma, sorry, the mu event mu is coming out of the recover class, and then others are 0. So we run this as well. So you can check the EMATs if you want. So you have it, the matrix 3. A 6 by 3 matrix. 6 by 3 matrix. So you can check. And then you have the Gillespie function, Gillespie, which contains all the arguments that we have there. You also run that. So, and then we have the parameters in the model. We have the initial values, 100, 100 is for susceptible, and the I is 2, and the R is 0. Then the simulation. So I simulate. So I want to see what is inside that. I have sim. I run the sim. Inside the sim, I have all of this. That's the so I have the time, and then I have the S, and then I have the I have the R. So the time is the first one, which is called sim. You know, if I want to call anything there, let's take for instance, I want a sim. Sim, comma 1. It gives me the time, everything about the time step from 0 to 500. And then I want to see other ones. Another way to do that is also to say sim time. You can do that like that. You will see everything to one, and then you say sim, comma 2. You want to see everything on the S class. And then maybe sim, you want to see S. Same, and either of the two. Same. So we are looking here. We want to plot. This. That's a. We want to plot time against SIR. We want to have everything, all the whole classes in a particular graph. And then I need to now I run this. So you have what I'm having here. So I have about 3 different colors, which is green, red, and black. So we are going to talk about this. What are they really saying? Now, and then I needed to put the legend. So you can decide to put the legend top right, top left, depending on where you want it. So put the legend. The legend is too wide for me. Too wide. So I'm going to use something to reduce it. So if you type legend, you can always find them. If you type legend, you see all the what's it called? All the options or all the arguments. It's a function. So take for instance, this is legend. Legend, sorry. you can find out what are the things you need to see inside. So these are various arguments in level. So some of them we have used, some of them we didn't use now because it's not everything we need. So I need this one now because I need to reduce the character. Look at the way it was giving me the character. So I need the character expansion factor relative to the current per sex. So use for text and provide the default for this. So I'm going to use this. I can start with 0.1 depending on what I want to see. And then I plot. So it's very small. You can see it's very small. So I will increase it. It's very small. You can see the legend, very small. But let me put it to like 0.3. 0.3. So it's bigger now. You can see it's bigger a bit. Try to put 0.35, maybe to see better. So you can see S is the black and I is the red and R is the green. So you find out that the susceptible in this plot, this is a time series plot, but given by a stochastic event-based simulation. So you find out that there are ranges in the values of the susceptible population. Normally, you are supposed to have a straight line for a deterministic model. It's always straight. But because this is a stochastic model, you are having a lot of noise. You can see the variances and all of that in the model. Now, what you observe here is that the S, you see the susceptible population at certain time, they are shooting up. There's a peak, especially at the beginning, because the population that we use, what was our initial condition? Our initial condition was around, is it 500 or 1,000? 100, yes, so 100. So we had, so at the beginning they were more, and then at certain time they began to drop. So the susceptible started dropping because some of them are being infected. And then you are seeing here, you will see that at certain points, if you take maybe time between 0 and 1, you have a range of susceptible population at any given susceptible population, maybe at time 1. If you look at it at time 1, you have different values at a particular range. It's not the same way you will use for a deterministic model. You will see some randomness, the wave are not the kind of wave you are seeing in a deterministic model. Now, if you also look at the infectious class, the infectious class is also having that kind of randomness so there are fluctuations around. Look at this. So these are fluctuations, and then with that you find out that instead of getting a fixed value, you are going to have a range. At this point now, you have a range of a number of people that are infected at that particular time. So, and then if you also look at for the SIR, let me go back to the slide. Now, the Gillespie algorithm provides an exact stochastic simulation in the sense that the time evolution of the system is changing exactly according to the exponential waiting time distribution of the stochastic differential equation. Now, it is, however, computationally intensive. Now, what you can do here is that also, if we decide to, this one is 1,000, you see that the number of times we are running that Gillespie is 1,000 times. But if I decide to, let's assume that I'm reducing it to 100. Let's see what will happen. If I reduce it to 100 number of times, see that it's changing. 100, see that it's changing. Now, if I reduce it to 10, number of time, simulation. Now, it's also changing. That it. Now, if I increase it to 10, maybe 1,000, 1,000, I'm coming, are we 1,000? Yeah, you have it here. So, and then if I increase it to 2,000, so you see that it's not the same. See now, changing. Yeah. So you see the noise. So these are stochastic noise. So at very short interval, and then if you look at this place, you see what is going on there. Now it's not deterministic. Now you also see that if I also increase maybe 3,000, let's see. See, so it's changing from as you increase the number of times you run the simulation. You have different features of what is going on in the system. Now, so we'll look further at now it is, however, okay, the Gillespie-Style-Leap method uses the Poisson approximation instead of the exponential. What's the Poisson? The Poisson estimation is the waiting time, like the one we use for queuing. You understand? So approximation corresponds to the discussion of earlier section. If you assume that the interval that is between T1 and T0 is sufficiently short that any change in the rates are negligible. They are very small. So the number of events should be Poisson. Now, the time between somebody is infected and is infecting somebody, if you assume that it's very short, then we should be looking at Poisson distribution. You understand? So, especially in a closed system where people are not, if you put, take for instance in the primary school where the children, now in this place now it's difficult for adults to be putting, you cannot sit down beside somebody and you're putting your hand in that person's mouth. You understand? The person would likely say, are you okay? You understand? But a place where you are having primary school, in the primary school, somebody is, somebody will touch your mouth, and then because of that, the children are getting infected. They have a close contact with each other. So in that situation, you find that the disease spread very fast. Now, with mean overall rates and multinomially divided among the events according to their relative rates. Now, we write the general Tau-Leap simulator and then apply it to the SIR model. So for the SIR, it's different from the SIR. The SIR will have 8 events. So in the SIR case, we are having still what has happened there is that we have added another class he. So to the class, to the existing one, so the event you are having instead of 6, it has increased to 8. So in the first case, we have the rate mu n, which is the bet, and then we still have death, the natural death, and we have the the rate at which people die, and then we also have x minus I and e plus 1. Now the x minus I has to do with transmission. So the rate at which people are getting infected. So it goes out of x and goes into e this time, not I. And then we also have mu. The mu e is that's the death of the exposed or the pre-infectious. And then people go out of the pre-infectious and move to the I class through what we call the progression rates. People progress after some time from just being infected to become symptomatically infectious. So, and then at that point in time, the pathogen has incubated. The incubation period has ended, so the person is showing symptoms. So the I there, the mu I is natural death. So in the class of the I, people die and then they are moving out. So, and then the 7th event is I minus 1, and then R, which is at rate gamma I. So which means that people get recovered and move from I to R, and then mu R from death. So we have 8 events there, and then so we are going to have this kind of event matrix. Instead of 3, it's going to be 4. So that means number of this thing is going to be 8 by 4. So 8 by 4 matrix. Now, because we have 4 classes but 8 different events, and then you are going to have this kind of matrix. Now, the SIR equation is associated with each event, and you have this R list code. Just this. The only change there is that we have added the E class. So still same kind of code. I think I've also sent this one as well. And then we run, and then we are going to have something like this. Maybe so. Do you have the code with you? Okay, so so I have this the same, but just added. I'm using the mic. You cannot hear from the back. Okay. Okay. So we run that, and then we can check. The EMAT 2. So we have the matrix. We have the matrix, and then we also have the R list 2. So you have all the events, 8 events, R lists. I want to check each of them, what is inside. And then we have the tau. And then we assume an initial population comprised of 1,000 individuals. So one person has just been infected. And you see, that's why if you look at our initial conditions, you see one of the reasons why usually write that the initial conditions, you see that S should be strictly greater than 0, and then E can be greater than or equal to 0, and then that I should be strictly greater than 0, and R should be greater than or equal to 0. So because at the initial time, you find out that there are some persons in the population, especially who are susceptible, and then one person has been infected. So if there is no infection, you can't have a transmission model. So you also have, and then, yeah, so we have the plots. So we are having SEIR. So this is a stochastic base time series plots for SEIR. And then I'm adding a legend to see what is S. S is black, E is red, and I is green, and R is blue. So you find that at certain time, people who are population of people who are recovered, they went up and then maintained a kind of steady state, but a wave-like one. And then you find out that the population of exposed, or is exposed now, yes, they were increasing and then started dropping. And certain time, they dropped. That's a trough. This is a trough. This is a peak, and then maintain a kind of unpredictable behavior. So we can as well do the same thing we did the other time by taking range. That was 2 before. Let me say 10 now. And then let's see what comes out. Changing. Yeah. Changing. You see? So it was 10 now. You see the change? This is highly chaotic. So you see that everything is changing there. Maybe, if I decide to also increase again, maybe to 20. So it takes more time. So, okay, see the change. Can you see? Changing. Now I decide to increase it again to 30. It's going to take more time because you are asking it to run 30 times. Okay. Changing is getting more chaotic and unpredictable. So this is very strong. So, and then changing to 40. So I'm going to go after now to 100. It will take more time. Okay. Yes, so somehow now, crazy ones. Not so. So let me change to 35. Wow. Yeah. So this is, yeah. So you find out that you know the that you are going to have for each of the classes are going to, so you can easily say between 20 and 30 cases, between 40 and 50 cases, because of the random, this is random situation punctuation is going on here. So now we need to move forward. So I want to quickly discuss on stochastic differential equation. Now, the one we have done is event-based stochastic simulation. But now, if you want to develop, you have a deterministic model, and you want to force stochasticity on the deterministic model from the scratch. So you go through these parts. The overview is introduction, probability, Brownian motion, Ito calculus. Now there are two types of stochastic differential equation. We have the Ito and the Kolmogorov. But I'll be talking about Ito this time, and then maybe in the next year school we'll talk about the Kolmogorov. Now we have an ordinary differential equation, dx equals to f of xt, xt naught equal to x naught. This is just an initial value problem, IVP, because it has initial condition. So the initial condition there is xt naught, which is equal to x naught. So now this can be written as this. Do you agree with that? You believe it? Right. Now, why did we do that? We just bring this one, this dt, cross multiply in your GSS1. And then you have this, right? And then on the integral form, you can take the integral of this because it's already having dx. You know, that's why we call integration anti, right? Some of you who did the further maths in secondary school, you'll be able to, and then in 100 level, you did calculus. Now, this one is going to be, so how did you arrive at this? Yes? How did you arrive from here to here? How did you arrive here? Yes? Constant. Evaluation of initial condition. Can you come and show me? Okay. How we move from here to here. Yes, I can call at random, so be prepared and look at me so that I can call you. Don't hide your face. So this is an interactive class. Can you clean the board? I have a, yes. So look at my face. I want to call somebody next. If some people are afraid, okay, go ahead. Okay. Give me mic and then.
Hello. Okay, so okay. So we'll take the integral of both sides. We'll have integral of dx equal to integral of f of x comma t dt. So when you integrate dx, you have x equal to, when you integrate this function, this is a function of a function. So you introduce what we call dummy variable. So the dummy variable here, as they use there, is, since s is a function of t, the integral of this will give us x, no, I'm sorry, will give us f, a function of, will give us integral of f, a function of s and t dx from 0 to t0, then plus constant of integration. So at this point, we now evaluate the boundary condition.
Where did you see the boundary condition?
From here.
No, that's initial, because if you say boundary condition, that's another problem.
Okay, initial conditions.
So for a boundary so you are talking a boundary value problem. So
this initial value problem. So we take the initial condition and evaluate. So at t equal to 0, we have s of t0 equal to, when you take this at t equal to 0, you have integral from, oh, I'm sorry, this is from 0 to t initially. I made a mistake here. 0 to, so when you evaluate, you now have from 0 to t0 of f of x comma t0 dx plus c. You now make c the set of formula.
okay.
Okay, I think I'm done.
So do you agree with him?
What is missing now?
No. I want to know, do we agree with him? So if you are saying no, let me see your hand. Oh God. If you are saying no, let me see your hand up. No, let him raise up his hand. You are saying no from that side. Okay. Shagu, you are saying no. Okay, come. Yes. Come.
So that c is equal to this. We have to
Okay.
replace c.
All right. You also said no. Are you saying no? Oh.
So
Leo, what's your conclusion? You said no. Okay. Yes. Can you come? Okay. Can you give him the, so let him show why he's saying no. Okay, give him the pen.
Good afternoon, everyone. So first off, this is, let's say, a differential equation. So we are trying to integrate it. So what we did is, we are supposed to integrate from the initial point, which was t naught, and integrate it to maybe t. So that was the first thing we were supposed to do here. So if you integrate dx, it's not trivial. In fact, the theorem why it holds.
Just go on. So he has written a paper. So this guy saw the paper and was trying to do what? No, not review. He want to. They are not talking though. He's trying to improve on the work. So let's see how he can improve. The PDF, okay. No, it's just the X, the T. Yeah, this is just the. Yeah.
So, will be from T naught to t dx. So the thing is, since x is, we are integrating. You said you said it's a single is in fact a multivariable function, x and t. We are in this case, we are just integrating with respect to t. Since x is a dummy variable, we can replace it with s, like we did the other time.
Yeah.
So it will be something like s, maybe say t ds.
You don't need to put c there again. Just f of x comma s. You understand?
Yes. Maybe
S of x comma s, yeah. Yeah.
something like this. So, of course, if we integrate dx, you get x, and if you put the what's the name, the limit.
The limit, yeah.
Don't forget that this x is a function of t. So we have something like x of t from t naught to t, and this is equal to this quantity here, this integral. So if I'm to write it, I have t naught f. So of course, if you put this the limit, you still have something like
Put
x
it, let's see
of
now.
t minus x of t naught equals this whole stuff. So you bring this one to the other side, then you'd have f of x of t equals.
Yeah. Thank you. So the two papers have been published. So we just need to improve on what we have. He has done it to an extent, and then we need to, yeah. So this is this one's supposed to come to this side, right? So it become x of t equals to x of t naught plus the integral t naught to t f of x of s comma s ds. So what kind of integral do we call this kind of integral? I didn't hear you. If you are speaking, can you talk to me? What kind of integral is that? Leo? What do you mean by definite? What kind of integral? Voterake?
Picard iteration, sir. Picard.
No, the integral. I'm talking of this integral, just this integral. When you have t naught to t on an integral, what do you call that kind of what do you call it? So that's a layman language. You are a mathematician, so you should tell me. That's Riemann integral. So you do the partition in the domain, the Riemann integral. Okay. Okay, so now can you show me the slide? Now a simple example is this: the x t equal to a of t, x of t, then x t naught equals to x naught. Now, when you are writing your model and your model does not have initial condition, you are not a good mathematician. You are not a good mathematician. And if your initial condition is wrong, you are also a bad mathematician. Now, because what you are telling us is that your model does not have solution. Yes. It means your model does not have solution because the solution of your model depends on your initial condition. So that's what tells us whether the solution exists, is unique, and continuously depend on the initial condition. So you talk about the well-posedness, the law of well-posedness. So it means that your model is not well defined when it doesn't have initial condition. So this is just Malthus' model for the growth of a population X. Malthus was a reverend, and I think an Anglican reverend. He thought about this and then developed this model. So this is the a there, a of t, x of t can grow because this is positive, so it can grow exponentially, right? The a there can be an intrinsic growth rate. between A can be bet minus det. Okay? So usually one consider that A of t is a deterministic parameter. That's the normal thing we do. So once it's deterministic, we fix it. So, but many times due to errors in measurements, variability in the population, and other factors that introduce uncertainties, we can think of A of t as a random variable. Now, the A of t here, dx over dt equals to A of t, x of t naught equals to x naught. So A of t, most time, I call it the intrinsic growth rate. The intrinsic growth rate is the difference between the bet and the det. So most time we said it's deterministic, it's fixed. You fix it. But in reality, it always follows a random variable. So we said that there are a lot of uncertainties around it. So we can think of it as A of t as a random variable. So if we subject it to a random variable, that's why I was saying that you can pick any of the parameter in your model, just like maybe gamma or any of it. You feel that there are some uncertainty around it, like beta, the transmission rate. So you subject the transmission rates to some stochastic fluctuation. Then you're having a random variable which has these features. So the A of t will now be A naught of t plus h of t psi of t, where A naught of t is the expected value or mean, and psi of t is a white noise. The white noise is a collection of stochastic fluctuation. Now, so later we will define this term. So if we define dw of t, that is dw of t is equal to psi of t dt, where dw of t is the differential form of the Brownian motion, we get dx of t, which is going to be that this one is equal to dx equal to A of t, x of t dt. Right? That's the first thing we write about it. And then once we induce stochasticity into A of t, then this one is going to become A naught. A naught of t, x of t, plus h of t, x of t, d omega of dw of t. Now, which means that you have, so the A naught here is due to this, what we have done to A of t. So if it means that we are now going to multiply. What we did here was to, since A of t is equal to A naught plus h of t psi of t, right? So we now say that x of t times, so for us to have A of t, x of t, we are going to have A naught plus h of t psi of t multiplied by x of t. Multiplied by x of t. So in other words, this one is going to be A naught of t multiplied by x of t plus h of t, x of t, psi of t. And we said that dw of t, dt. So dw of t is equal to psi of t dt. So in other words, we have A naught of t, x of t, plus h of t, s of t is equal to dw of t. So now this particular expression has become, can you come to this thing? So where the dw of t is the differential form of the Brownian motion. So we get this. So if you want to write a general form, a general stochastic differential equation for this, so this is a stochastic differential equation ready. So but a general form will be that, so it's not going to be f of the whole of this will be f of xt omega comma t, because this is influenced by stochasticity, plus this one g of xt omega comma t dw of t. So this is a general stochastic differential equation for any one-dimensional system that have that kind of picture. Maybe, for example, I'm saying that my dx of t, dx dt is equal to f of xt, starting from there. So my dx dt is equal to f of xt. My f of xt here is what? Is a of t, x of t. Right? So the other addendum here, like I'm saying that this is my f of xt, f of x comma omega now because of the noise, and then this one is g of x comma omega. So that gives a kind of general t comma omega, a general differential equation, stochastic differential equation where omega is an element of the sample space, and x is this x here is, which is also this, is random variable or stochastic process. Here we take the initial condition is x naught comma omega, that means t is 0. That's why x of t comma omega, t is 0. So we have x naught to be known with probability 1. Now the equation is equivalent to the integral equation. That x of is just like the first one we did there. Sorry. Just like this. But this time we have added the Brownian motion. So it's turning to a stochastic differential equation. And so the equation is equivalent to the integral equation, this. So later we'll see what is the meaning of the stochastic integral and what is a Brownian motion. Now, concept of probability, because stochastic processes or stochastic differential equation is based on probability and the theory of probability. So the result of a game or an experiment is many times random. You agree with that? If you want to check, if you have a die, you throw it. If you throw it 5 times, are you sure you are going to get the same kind of number? So it's unpredictable. So now, for example, we toss a coin. The possible results are head or tail, or head or tail. They are not predictable. Now, the sample space, which is this for a coin, is either head or tail. If you throw it 20 times, you are likely to get different variables. So the events are the subset of, which is the sample space. In your set theory is called the universal set, but in probability we call it the sample space. So, and then you have the singleton set of H, which is the head. So it means that you can have one head and then tail, head, tail, and then you have the empty set. So if the coin is not loaded, the probability of a head, my time is up. Okay, let me just finish this part. So if the coin is not loaded, the probability of a head is 1/2. And the probability of a tail is also 1/2. So that is, if we toss the coin many times, we expect to get heads half the time. I'm going to stop here. So we continue.